Hello everyone, welcome to our first video on probability. I'm Nick Stugard and I'm really happy to be here with you. In this video, we'll cover most of sections 5.1 and 5.2, so let's get started. Let's start with the fundamental question. What is probability? Essentially, probability is the study of how likely a particular event is to happen. This topic is one of the most mathematically rigorous sections in our statistics course because probability relies heavily on numerical reasoning. Our natural instincts aren't always reliable when we're estimating probabilities. So we need math to kind of give us this more structured approach. It really helps us where our intuition tends to fail. To introduce this concept, let's go through a few examples that highlight key ideas we'll be working with. Our first example is a really well-known thought experiment. It goes a little something like this. Linda is 31 years old, single, outspoken, and from a middle-class background. She majored in philosophy and was deeply invested in social issues as a student. She also actively participated in anti-nuclear power demonstrations. Given this information, which of the following is more probable? Either A, Linda is a bank teller, or B, Linda is a bank teller and is active in the feminist movement. Take a moment to think about your answer, and we'll get back to it in 3, 2, 1. The correct answer is A. Linda is more likely to be just a bank teller. If you picked B, don't worry. This question has been widely studied over the past 40 years, and research shows that more than 80% of people tend to answer incorrectly. The reason for this common mistake is how our brains interpret information. Just like I said, intuition kind of tends to fail us when it comes to probability. Based on Linda's background, it seems obvious that she is involved in feminist causes. However, in probability, the word "and" means that both conditions must be true at the same time. So the likelihood of her being both a bank teller and a feminist is inherently lower than the likelihood of her being just a bank teller. When discussing probability, the word "and" has a very specific meaning. It signifies that both conditions must be true simultaneously. So is it more probable that Linda is both a bank teller and a feminist? To be classified as both, she must meet both criteria at the same time. While her background might strongly suggest she is a feminist, the probability of her being only a bank teller is still greater. Even if just one bank teller exists who matches her description but is not a feminist, the likelihood of her simply being a bank teller remains higher than the probability of her being both. In general, it's always more probable for someone to fit into a single category rather than two. Let's move on to another example. Which of the following statements seems the most reasonable? A, I just flipped 3 heads in a row with a fair coin. My next flip is very likely to also be heads. I'm on a winning streak. B, I rolled a fair 6-sided die 10 times, and I never rolled a 6. The next roll is especially likely to be a 6 because I'm due for one. Or C, it usually rains in New York. Usually, if it rains in New York, it rains here a couple hours later. It just started raining in New York, so it will probably rain here soon. Take a minute and think about it, and we'll get back to it in 3, 2, 1. The correct answer is C. It will likely rain here soon. This is because, unlike the other two statements, this one is based on a logical pattern rather than a faulty assumption about probability. People often believe in things like hot streaks or the idea that something is due to happen simply because it hasn't occurred in a while. However, this is just our intuition and memory influencing our judgment. Think about it. Can a coin remember how it landed in previous flips? Does it somehow know that it landed on heads 3 times in a row and therefore wants to continue landing on heads? No. A coin has no memory. We're the ones who remember the results. The same logic applies to rolling a die. The die doesn't keep track of past rolls, meaning each roll is independent and the probability remains the same every time. Despite this, people often assign human emotions and patterns to things that are just entirely random. Now let's consider another scenario. Which of these events is more likely? Winning the Powerball jackpot or rolling a die 20 times and landing on 6 every single time? Both sound nearly impossible, but which one is actually more probable? Take a moment and think about it for 3, 2, 1. Mathematically, the odds of winning the Powerball jackpot are 1 in 292,201,331, which is an incredibly slim chance. That's a 0.000000342%. However, the probability of rolling 20 consecutive sixes, is 1 in 3,656 trillion, a number that is so large it's difficult for us to even comprehend. In fact, 3.65 quadrillion is not even a unit of measurement we can typically use in everyday life. When you compare the two, it becomes clear that winning the Powerball, while extremely unlikely, is still far more probable than rolling 20 sixes in a row. The sheer number of zeros in that probability highlights just how rare such an outcome would be. But how do we actually calculate these probabilities? How do we determine these values mathematically? That's where probability theory comes in. As we move through Chapter 5, we'll delve deeper into the mathematical principles that allow us to quantify probabilities. Before we get into more complex concepts, let's start with some basics. Probability is something we encounter in everyday life, even if we don't always think about it explicitly. For example, when I was pregnant, I began to think about the probability that I would have a girl. What are the chances that the baby will be a girl? Many people express probability in terms of ratios. There's a 50-50 chance of having a girl. That's a reasonable way to describe it. There are 2 possible outcomes, so the likelihood of each is 50%. While this is a common and valid way of thinking about probability, in this class, we'll mostly focus on 2 specific ways of expressing probability, as proportions and as decimals. A proportion represents the part relative to the whole. In this case, the probability of having a girl is determined by considering both possible outcomes, boy or girl. Since there are 2 equally likely possibilities, the proportion is 1/2. Similarly, probability can also be expressed as a decimal. If we divide 1 by 2, we get 0.5, which is the probability of having a girl. While percentages are often used in everyday life and everyday conversations because they're more intuitive, in probability calculations, we primarily use proportions and decimals. Almost all of this course will be expressed in one of these 2 formats. Now let's define probability more formally. Probability represents the long-term proportion of observing a certain outcome. The phrase long-term is crucial here, and we'll explore its significance more in detail soon. When discussing probability, any event's likelihood always falls between 0 and 1, or equivalently, between 0% and 100%. A probability of 0 or 0% means the event is impossible. It simply cannot happen. Conversely, a probability of 1 or 100% means an event is certain. It must occur. We'll also frequently discuss the concept of unusual events throughout this class, as identifying unusual occurrences is fundamental to research and statistics. However, there is no universally fixed threshold for what qualifies as unusual. It depends on the context. In this course, we'll often use 0.5 or 5% as the standard cutoff, meaning that if something happens less than 5% of the time, we'll typically classify it as unusual. This is a common benchmark in social sciences, polling, and similar fields. Another key principle in probability is that the sum of all possible outcomes must equal 1 or 100%. For example, when flipping a coin, the 2 possible outcomes are heads or tails. Since each outcome has a 50% probability, their sum is 50% plus 50% equals 100%, or 0.5 plus 0.5 equals 1. Now let's explore how sample size affects probability calculations. When I gave birth, I stayed in the hospital for 2 days. During that time, 15 girls and 8 boys were born. That means there were 23 total births. The proportion of girls born is 15 girls out of those 23 total births, giving me a probability of 0.652 or 65.2%. Hold on, does that mean this is how likely it is for girls to be born? This seems significantly higher than the expected 50%. So is the probability of having a girl 65%? Not at all. We know that the true probability is 50%. But why did this turn out wrong? Why didn't these babies listen to the way math is supposed to work? Well, the discrepancy occurs because our sample size is too small to reflect the true probability accurately. So let's explore this a bit more. Now let's expand our data to a larger sample size. Looking at the entire year's births records at the same hospital, there were 527 girls born and 514 boys born in that time, giving us a total number of births of 1,041, and the proportion of girls born, 527 girls out of that 1,041, gives us a probability of 0.506 or 50.6%. While there were still slightly more girls than boys, this proportion is much closer to the expected 50%. The difference here is that a larger sample size gives a more accurate representation of probability. And this concept is a key principle in statistics. Small sample sizes can produce misleading results, but as the sample size increases, observed probabilities tend to align more closely with their true values. So what's the key takeaway here? Sample size matters. We need a large enough sample to ensure that our statistics accurately reflect reality. This concept is tied to a fundamental principle in probability known as the law of large numbers. The law of large numbers states that as the number of trials in a probability experiment increases, the observed proportion of outcomes will get closer to the actual probability. In simple terms, if you want to get a reliable estimate of probability, you need a large sample of data. You've got to ask a lot of people. This concept is sometimes called the wisdom of the crowds. If you ask just one person a question, they might be wrong. But if you ask 1,000 people, their collective answers are likely to be much closer to the truth. This principle underpins many statistical techniques, especially in polling and research. Now that we understand why probability calculations require a solid foundation, let's talk about the three main ways we calculate probability. The first is classical probability. This method is based on logic and counting techniques rather than experiments. For example, if we assume an equal chance of having a boy or a girl at birth, the probability of having a girl is 50%. This approach doesn't rely on data collection. It simply assumes all outcomes are equally likely. The second way is empirical probability. This method is based on actual observations and recorded data. For example, tracking hospital births for a year and calculating the proportion of girls born would give us an empirical probability. Unlike classical probability, this approach relies on real-world data rather than theoretical assumptions. The last is called subjective probability. This method is based on expert judgment and estimation rather than strict mathematical calculations. For example, a meteorologist predicting a 20% chance of rain, or a sports analyst estimating that the Patriots have a 20% chance of making it to the Super Bowl. These probabilities are based on past knowledge and expert intuition rather than precise mathematical formulas. However, while subjective probability is commonly used in fields like meteorology, economics, and sports analytics, we won't be using it in this course. Since it isn't mathematically rigorous, we will focus on classical and empirical probability. Before we dive into more examples, let's go over a few key definitions. The sample space, which we denote S, represents all possible outcomes in a probability experiment. An event, denoted as E, is a specific collection of one or more outcomes that we are interested in analyzing. And then, of course, the probability of an event, which we denote P of E, where E represents our event, is calculated as the number of favorable outcomes divided by the total number of possible outcomes, which is where this formula comes in handy. Okay, so we need to think about the size of our sample space and the size of the event actually occurring. For example, if we consider the probability of a baby being born a girl, I could denote that where my event is the baby being a girl. So the probability of the baby being a girl equals the size of my event of a girl being born over the size of my sample space. So since there are two possible outcomes, boy or girl, right? My sample space is 2, and then the event of having a girl is one of those two outcomes. Therefore, the probability of having a girl is 1/2, or 0.5, or 50%. Now let's apply these principles to an example. What is the probability that a randomly chosen month starts with the letter J? Well, the first thing we need to do is determine the sample space, right? So the total number of months in a year is 12. So our sample space, which we denote with our S, and we can list out in brackets here, is January, February, March, April, May, June, July, August, September, October, November, and December. That's all of the months that we could possibly have, right? We have to consider all of the months in this sample. Next, the specific event that we're interested, right, we need to identify that event, is months that start with the letter J, okay? And there, that event, right, months that start with the letter J, all possible outcomes are January, June, and July. So there's 3 possible months that start with J. Therefore, the probability is, we just plug it right into that formula, the probability of our event, which means the probability that a month starts with the letter J, is 3 possible outcomes out of 12 outcomes in all, or 1/4. There's an important detail to keep in mind. While 3/12 is correct, most probability platforms like MyStatLab require answers in a simplified form. So we would reduce this to 1/4, which is the correct way to express the proportion. If you're asked for a decimal, you would divide 1 by 4 to give you 0.25, or 25%. In everyday conversations, percentages tend to be easier for us to interpret. Saying that there's a 25% chance of selecting a J month is often more intuitive than stating 1 out of 4, or 0.25. However, when answering probability questions in MyStatLab or other assignments, always double check the format required, because it can be very persnickety if it is looking for something specific. If they ask for a proportion, simplify the fraction. Okay, so it would be 1/4. If they ask for a decimal, round it to the specified number of places, and MyStatLab will tell you 1 decimal place, 2 decimal place, 3 decimal places. Being mindful of these formatting expectations will help ensure your answers are marked correct. Now let's look at our second example. What is the probability of having a son followed by 2 daughters? In this case, I have 3 children, right? First, second, third child. My oldest is a boy, and my next 2 are girls. So how do we determine the probability of this specific birth order? And it's really important to recognize that birth order is specified here. It's a boy and then 2 girls. First, we need to define our sample space, right, as always, which includes all possible birth orders for 3 children. Right now, we won't use advanced counting techniques. We'll simply build the sample space step by step. So each child can be either a boy or a girl. I want to visualize all possible outcomes 1 step at a time. Let's think about the first child. The first child could be either a boy or a girl. The second child, regardless of what the first child is, could be either a boy or a girl again, independent of the previous 2. This branching process gives us every possible birth order if we systematically list them. So if we go into our third child, which could also be a boy or a girl, we wind up seeing each of these represents a different possibility. And so my total number of outcomes, my sample space here, is represented in this column. I could have a boy, 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 a boy, boy, girl, a boy, girl, boy, and I'm just reading across, right? Boy, 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 girl, boy, girl, boy, and so on and so forth, giving us a total of 8 possibilities. So our sample size is a size 8. And it's important to recognize the difference between a sample and a sample size. A sample represents all possibilities listed. A sample size means when we list out all those possibilities, how many are there? So this is our sample, and since there are 8 possibilities, our sample size is 8. Now let's find the probability of the specific outcome where the birth order is boy, girl, girl. If we look back at our list, we see that only one of the 8 outcomes fits this description. Therefore, the probability is, again, the size of that event occurring over the size of the sample space, which we have 1 possibility of the 8 total possibilities in our sample space, meaning the probability is 1/8, or 0.125, or 12.5%. Now let's slightly modify the question. What is the probability of having one boy and two girls? Notice, this time we don't care about birth order, just that we have exactly one boy and exactly two girls. The sample is still the same as the previous example with a size of 8 because we're still talking about 3 children, whether they're boys or girls. However, the event size is different since order does not matter. There are now 3 possible outcomes that match this description: boy, girl, 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 boy, girl, or girl, girl, boy. Since 3 of our 8 outcomes fit our criteria, we have a different probability. Our probability now becomes the size of our event, having 2 girls and 1 boy. There's 3 possible outcomes for that, out of our 8 possible outcomes for our sample space, giving us a probability of 0.375 or 37.5%. So even though these two probability questions seem very similar, they ask different things. The first question asked for a specific birth order of boy, girl, girl, so there was only one outcome counted. However, the second question asked for any order with one boy and 2 girls, so we had 3 possible outcomes. This demonstrates a crucial concept in probability. Order matters in some problems, but not in others. As we continue working with probability, always read questions carefully to determine whether order is important. Misunderstanding this detail can lead to incorrect calculations, so paying close attention to how questions are worded is essential. Now let's go over a few more key definitions. First, we have disjoint events. Disjoint events are events that cannot happen at the same time. In other words, 2 events are disjoint or mutually exclusive if they have no outcomes in common. For example, let's consider the set of whole counting numbers from 1 to 6, the numbers 1, 2, 3, 4, 5, 6. If I were to randomly pick one of these numbers, think about the probabilities of getting an odd number and the probability of getting a 6. And I've got a little visual to go along with it. Here in this loop right here, loop A, we have all of the odd numbers. Here in loop B, we have all the numbers that are 6, and then outside of it we have any numbers that's not odd or a 6. You can see there is absolutely no overlap between these two sets because it's impossible to pick a number that is both odd and a 6 at the same time. 6 will never be odd. So these two events are disjoint. They cannot occur simultaneously. Let's next clarify the meanings of the words and or in probability, since they don't always align with how we use them in everyday language. The word and refers to an intersection, meaning both events must happen at the same time. They can occur simultaneously. In probability notation, and is often represented by this symbol right here. It looks like an upside down U. For example, if we again considered that same set of whole counting numbers from 1 to 6, right? 1, 2, 3, 4, 5, 6. What is the probability a randomly selected number is both over 4 and odd? Okay, if we are considering both of those conditions when we pick that number. And so again, I have my two sets of numbers that are over 4, which is 5 and 6, and numbers that are odd, 1, 3, and 5. Notice there is an overlap here because we have one number that is both over 4 and odd, and that happens to be number 5. It belongs in both of those sets, and so it is within the intersection. Okay, it meets both of those conditions simultaneously at the same time. On the other hand, the word or refers to a union of two events, meaning either one or both can occur. In probability notation, either the number is over 4 or an odd number. We count any number who meets at least one of these criteria. And so we notate or denote this with this U for union, which is a great way to remember it. It looks like a U, it stands for union. You'll often see this symbol in textbooks or in my stat lab. Now, whether or not two events are disjoint affects how we calculate their probabilities. So it's really important to understand and always take the time to ask ourselves, are these two events disjoint? Meaning, can they possibly occur at the same exact time simultaneously? If not, then they're disjoint events, and we use the addition rule for disjoint events. So if events E and F are disjoint, we calculate the probability using this formula. The probability of E or F, notice that word or, equals the probability of E plus the probability of F. This is one of the most fundamental rules in probability. So if I go back to that example from the previous slide, if I'm considering the countable whole numbers from 1 to 6, what is the probability of getting an odd number or getting a 6? We know these events are disjoint, right? Because we cannot have, 6 will never be odd. So we can use this formula to calculate that probability. So if I plug things in, right, the probability of getting a 1, the probability of getting an odd number or the probability of getting a 6, I just plug right in. So the probability of getting an odd number, I've got 1, 2, 3 possible odd numbers out of 6 total numbers. The probability of getting a 6, I've got 1 possibility out of 6 total possibilities in my sample space. And if I add those together, that gives me 4 out of 6, or 0.67 or 67%. So we can use this addition rule for disjoint events. Before we apply this rule in another example, let's make sure we all have a basic understanding of a standard deck of playing cards. So a standard deck of cards consists of 52 cards in all. There are 4 suits. We've got hearts, diamonds, clubs, and spades. And then each suit contains 13 cards in all, okay? So we've got our face cards, which are Jack, Queen, King, and Ace. And then we have the numbers from 2 through 10. If you're unfamiliar with the structure of a deck of cards, refer to an image for reference, as many probability problems involve card decks, and you can use this one to refer back to. Now let's apply the addition rule for disjoint events using a deck of cards. For example, what is the probability of drawing a Jack, Queen, or King from a standard deck of cards? So our first step would be to identify the sample space. What is our sample and what is our sample size? Since we are drawing from a full deck of cards, our sample space size is 52, right? Our sample is all of those different cards. There's 52 of them, so the sample size is 52 here. Our next step is to determine the number of favorable outcomes, meaning, right, we draw a Jack, a Queen, or a King. So we need to think about how many events are there, what are the events, and are the events disjoint? There are 4 Jacks, 4 Queens, and 4 Kings in the deck, okay? These categories are disjoint because if I pull out a single card, that card cannot be both a Jack and a Queen, or a Queen and a King, and so on. So these events are disjoint, meaning we can use the addition rule for disjoint events. So since the events are disjoint, we simply use the addition rule for disjoint events and we add their probabilities together, their individual probabilities together. So the probability of getting a Jack or a Queen or a King equals the probability of drawing a Jack plus the probability of drawing a Queen plus the probability of drawing a King. Okay, each of those has a probability of 4 out of our 52 cards, right? There's 4 Jacks, there's 4 Queens, and there's 4 Kings in a standard deck of cards. There's 52 cards in a standard deck of cards, so these are their individual probabilities. If we add them together, we find that the probability of drawing a Jack or a Queen or a King is 12 out of 52. This reduces to 3 out of 13, which is our proportion. And if we wanted to put it in terms of a decimal or a probability, it would be 0.231, meaning a 23.1% chance. One last thing to watch out for, if you're completing a probability assignment in My Math Lab or another online system, make sure again to follow formatting instructions carefully. If they ask for a proportion, give a simplified fraction. If they ask for a decimal, round to the specified number of places. Okay, now let's move on to example 5. What is the probability of drawing a Jack or a club from a standard deck of 52 cards? And I want you to just notice that this example differs from the previous. We're going to use that same 3-step sequence where step 1, we identify the sample space. Step 2, we determine the number of favorable outcomes, right, for these events. And step 3, we determine the probability. So to begin, let's do step 1, let's identify our sample. So what is our sample and what is our sample size? Well, our sample is that standard deck of cards. meaning our sample size is 52 because the standard deck has 52 cards. So the size is 52. Now let's move into step 2, determine the number of favorable outcomes. So we need to think about how many events are there, what are the events, and are the events disjoint, right? So we have 2 events happening here, drawing a jack, drawing a club. Are these events disjoint? So I want you to take 10 seconds and think about that question. So hit pause and come back in 3, 2, 1. Here I've created a Venn diagram to kind of help us understand this visually. Venn diagrams are really helpful in probability because we can think of each event as a distinct set or circle here in our Venn. Okay, and our universe, this big rectangle, contains every possibility or our sample space. So notice for this particular problem, my universe, my sample space, has all of the cards in a standard deck of cards. Okay. On the left, my first set is my set of jacks, and on the right, my second set is the set of clubs. And so I go back to that question that I need to ask, are these events disjoint? Can these 2 conditions occur simultaneously, right? Can a card be both a jack and a club at the same time? Well, the answer is yes. We have a card in which this occurs, the jack of clubs. So these events can occur simultaneously, meaning my sets are not disjoint and there will be an overlap or an intersection here. Now you can see my overlapping sets. This middle overlap represents the intersection of my sets or events. Now that we have an understanding of this Venn diagram, let's sort our cards and calculate each probability. So I'm going to put my jacks in the jack set, my clubs in the club set, and then anything that's both a jack or a club is going to go in this intersection. Here you can see I've sorted my cards into their corresponding sets, right? I have all of my jacks here, all of my clubs here, and anything that is both a jack and a club at the same time goes in my intersection. So the probability of drawing a jack is 4 out of 52 because I have 1, 2, 3, 4 cards that are jacks. The probability of drawing a club is 13 out of 52 since there are 13 cards that are clubs. And notice there are 13 cards in this set right here. The probability of drawing the jack of clubs in my intersection is 1 out of 52 since it's counted in both categories. So now I can use the general addition rule, which is so named because you can always use it whether your events are disjoint or not. And we'll talk about that more in a minute. So the probability of drawing a jack or club is equivalent to the probability of drawing a jack plus the probability of drawing a club, and then we need to subtract off any card we might double count. So we need to subtract off that probability of drawing a card that's both a jack and a club at the same time. So the probability of drawing a jack or club becomes 4 out of 52, right? 4 out of 52 cards are jacks, plus 13 out of 52 because 13 out of our 52 cards are clubs. And then we need to subtract off that, that one card that's both a jack and a club so we don't double count it because it's been counted here and it's been counted here. So we need to subtract off one of those. Okay, so our 1 out of 52. Which gives us 16 out of 52. If we simplify that to a reduced proportion, we get 4 out of 13 as a probability, 0.308 or 30.8%, about a third of the time. Okay, so 30.8% of the time when I draw a random card from a standard deck of cards, I will draw a card that is either a jack or a club. This example demonstrates the importance of subtracting the overlapping probability to avoid counting the jack of clubs twice. So this brings us to the general addition rule, which applies to all probability problems, which I was kind of alluding to on that last slide, that involve 2 events, E and F, whether they are disjoint or not, okay? We can always use this. It always works. For disjoint events, the overlap right here is just 0. So subtracting 0 off doesn't affect the calculation. However, for non-disjoint events, this formula ensures we don't overcount. This is one of the most important rules in probability, and I highly recommend memorizing it. It will come up frequently throughout this chapter. The last concept we'll cover in this lesson is complements. So given a sample space S and an event E, the complement of E includes all outcomes not in E. We denote this as E to C, almost like an exponent. For example, in a deck of cards, if event E is drawing a club, right? Then E complement, the complement of E, represents everything that is not a club and would go out here, which would be all the hearts, diamonds, and spades. So only clubs would be in our set. The hearts, diamonds, and spades would be in our complement. As a key property of complements, we know that the probability of an event plus the probability of its complement equals 1. This simply means that either an event happens or it doesn't. There is no other possibility. So it represents 100% of the possibilities. If we take this formula and rearrange it, we can get the complement rule, which looks like this. The probability of the complement equals 1 minus the probability of the event. And this rule is extremely useful when calculating probabilities indirectly. Now let's look at one very quick and simple example of using the complement rule in action. The birth control pill is 98% effective in any given month. So what is the probability that the birth control pill does not work? Which is asking for the complement. And if it helps, I've put a little visual here in this corner to help you think about this problem, if you liked using the Venn diagrams from the previous example. So using the complement rule, right, the complement of the pill working is the pill failing, and we can plug right into that formula. The probability that the pill will fail is equal to 1 minus the probability that the pill works. We know that the probability the pill will work is 98%, or as a decimal, 0.98. So the probability that the pill fails will be equal to 1 minus 0.98, giving us 0.02 or 2%. So the probability of failure is 2%. This should make intuitive sense. If the pill works 98% of the time, then it must fail 2% of the time. This wraps up the basics of probability, and we're going to continue building off these concepts as we move further into Chapter 5. If you have any questions at all, please feel free to ask, and good luck on the homework.